So today we're going to learn about the p-value, which is the statistic that we use to try to reject or disprove the null hypothesis. I'm going to say disprove a lot in today's lecture, but when I say this, I'm talking about statistically disprove. That means there's a small chance that we could be wrong. But I need you to realize we're trying to disprove the null hypothesis that our two population means are the same or that our population mean difference is zero. All right, a simple thought question will show us why we're trying to disprove things in science. Prove to me that sheep are white. What are you going to need to do that? You would need to measure the color of all sheep ever from their evolutionary existence to their extinction. You might need a time machine. It's really impossible. Or let's take the related question. Disprove that sheep are white. You just need to find one sheep that's not white. Done. One of these is easier than the other. So science equals disproof. Good science equals disproof. Most scientists agree on this. And the goal of the p-value is to try to disprove the null hypothesis. And the null hypothesis is simply that the population mean difference equals zero. So we're trying to disprove that. I mean, we ran an experiment. We want to be able to disprove that. Now I'm going to talk a little bit about history. You can ignore me till I'm done. So where did the p-value come from? It's kind of interesting. Karl Popper came up with the idea that a good scientific theory needs to have an observation that can disprove it. Otherwise, the theory is untestable. And if a theory is untestable, it's not scientific. If a theory is untestable, it just will. And if it's a scientific theory that's untestable, there's no way to get rid of it if it's wrong. And we need to be able to get rid of wrong theories. Well, that's Popper's idea. And Popper also, what I love about Popper hated Freud and helped develop this idea because he hated Freud's theories because no observation could disprove Freud's theories. So I like to argue that Popper is in part responsible for us using the p-value because Popper created the idea that we have to disprove something in science. And then statisticians came along and eventually we started using the p-value to disprove the null hypothesis. The hypothesis that the population mean difference is zero. You've probably seen the population mean or the null hypothesis represented in different ways. One way is that the two population means are perfectly identical. Another way you've seen it is the mu1, the mean of group 1, is equal to mu2, the mean of group 2, the population mean. Mu is population mean. Or the mu of the control group, the mean of the control group at the population level equals the mu of the experimental group, the population mean of the experimental group. Those are equal. Some of us, like myself, do algebra to say the population mean of the control minus the population mean of the experimental group equals zero, or we can just say the population mean difference equals zero. We're trying to disprove this. How do we disprove the null hypothesis if that's our goal? How do we disprove that the true population mean difference equals zero? Well, we all kind of know part of the answer. We run an experiment, but we have to evaluate if the null hypothesis is true, which is a hypothesis about a population mean difference from one experiment, from one sampled mean difference. So we got to figure out how to connect sampled mean differences to the population mean difference that is presented in the null. It's complicated, but we're going to go over this on the next slide. So we now have to figure out how do we connect the null hypothesis, which is in regards to a population mean difference, to our sampled mean difference from our experiment, right? Sampled mean differences are not population mean differences. That's one of the things we have learned thus far. Well, first we have to realize what an experiment does. An experiment samples one mean difference from a population. So that's great. Okay, so they're kind of connected. We might start to see some connections here. So now let's imagine we knew the null were true. What are we likely to sample then? Well, when the null is true, we are very likely to sample a mean difference that is equal to 0 or near 0. Okay, let's take this a step further. I want you to imagine that we ran an infinite number of experiments. In terms of sampling language, imagine that we sampled an infinite number of mean differences. Infinite means infinite, okay? What would you expect to find in these mean differences? Well, if you're thinking about the null hypothesis being true, you would expect that many of these sampled mean differences would be 0 or near 0, right? If the null were true. We know that we will sample a few mean differences that are not very close to 0, just by chance, if the null were true, or if the population mean difference were 0. We know that as sampled mean differences move further and further away from 0, they become less and less likely to sample if the null were true. And yes, I know I said this just a few seconds ago, we will rarely sample a few very extreme mean differences that are drastically different from 0 if the null were true. When the true population mean difference is 0, if the null were true, those are the same thing. We basically have just described the normal curve. And so the normal curve is going to allow us to connect the null hypothesis, which is about a true population mean difference, to any sampled mean difference that we may get from any experiment. So the connection between our sampled mean differences and the null hypothesis is this normal curve. Now, this picture is not just a graphic to help you learn. I really want you to pay attention to it. This picture connects our null hypothesis to the sampled mean difference. So this graphic is just taking what we talked about in the last slide and turning it into a visual picture, a visual image. But this picture is so important that I want you to be able to draw it from memory. We called this distribution, this picture, the random sampling distribution of mean differences when the null is true. Now, this is a distribution or graph of all possible mean differences that we could sample if the null were true. Now, I want you to realize this. This distribution assumes the null is true. We're going to use this distribution to try to disprove that the null is true, so keep that in mind. This distribution is based on the ideas in the previous slide. It's not based on data that we collect, so it's make-believe. I think that's very important. And we use this distribution to tell us the probability of sampling any mean difference if the null were true, and this is where p-value is going to come from. This distribution has specific properties. So I just want to restate that it's a made-up distribution that assumes the null is true. So those are part of its properties. This distribution assumes the null is true, and it's made up. The building blocks of this distribution, the components, are actually sampled mean differences. And I want you to realize that, right? You can see them there in the ovals. Now, if the null hypothesis were true, the most commonly sampled mean difference is 0. You can see that line, that hump, the top of the hump and the line at 0. Well, that's the mean of the distribution. And why is that the mean? Because if the null were true, the most likely sampled mean difference is 0. It just makes sense. If the true population mean difference is 0, we are most likely to sample a mean difference of 0 as well. The shape of this distribution is normal. If you really want to know, this comes from something called the central limit theorem that shows that these distributions are normally shaped, but we can skip that. I just need you to know it's normal. The standard deviation of this distribution is called standard error. And so we know that standard deviations tell us, when we're looking at them in our experimental data, they tell us error in our data, noise in our data that we don't know where it came from. Well, in this case, what it tells us is error in our sampling, right? When the null is true, the standard error of this distribution is the standard deviation of this distribution, and it tells us the error of our sampling process. If we had no error in sampling, every single time we would sample the population mean difference of 0, right? Well, that's not the case. There is error in our sampling that's represented by the standard deviation of this distribution. If you don't get that, that's fine. What I need you to get is that the standard deviation is called standard error, and that standard error is just telling us the error in our sampling mean differences from the population. That's all it's telling us, right? The deviations from the population mean are errors in our sampling of mean differences. That's all you need to know. The limits of this distribution are negative infinity to positive infinity. That's great. So if we connect everything together, this is a probability distribution. It tells us the probability of sampling any mean difference from negative infinity to positive infinity if the null hypothesis were true. and this is the foundation of our p-value. And since we're trying to disprove that the null hypothesis is true, we're going to need to really use this distribution. This is so important, I'm going to restate it twice. The random sampling distribution of mean differences when the null is true is a probability ruler. We can use it to find the probability of sampling any mean difference from negative infinity to positive infinity when the null hypothesis is true. Let me show you how we use it. So I have just a problem, just a problem for you, just to see how we would use it. What is the probability of sampling a mean difference of exactly 0 if the null were true? Now I want to say something. Probability is just percentage divided by 100. So essentially I'm asking you a percentage question, but it's not going to be on the it's not going to be on a 100% scale. It's going to be on the scale of 1. Probabilities have a max value of 1. Percentage has a max value of 100. Okay? So what's the probability of sampling a mean difference that is exactly 0 based on my visual representation of the null hypothesis being true, right? This is the random sampling distribution of mean differences when the null is true. It's a distribution of all possible mean differences that we could sample when the null is true. What's the probability of sampling a mean difference of exactly 0? Well, it is all of these ovals that include the color red divided by all the ovals in the curve, which are all the ovals that include the color blue. If you notice, my red ovals are both red and blue because they are both part of the top and the bottom of this equation. They're both part of the numerator and denominator. So the probability of sampling a mean difference of exactly 0 would be this fraction, red over blue. We don't need to know the number, but we can look at that and be like, oh, that might be 10%. That's what we're probably thinking. Well, we're going to have to correct this in the next slide. So the problem with my picture here is that it's not drawn to scale. It's probably 1,000 or 10,000 or maybe 100,000 times too large. Specifically, my mean differences are drawn like 1,000 times too large. I'm not going to shrink them here because then they wouldn't be visible anymore. But essentially, the probability of sampling a mean difference that is exactly 0 is that line right there, that red line. And the probability of this is the area of a line. And anybody that's ever taken advanced geometry, I believe, knows that the area of a line is infinitesimally small. So what we know here is that we're still doing the same thing. I'm just saying, like, you got to look and you got to shrink my mean differences down about 100,000 times. But I still want them in your graph so you understand what's going on, right? But ultimately, the probability of sampling a mean difference that is exactly 0 is the area of a line, which is infinitesimally small, which means 0.0 to a billion, to a jillion, keep going past that. Right before infinity, put a 1 there. And so it's a really small probability. So the probability of sampling any individual, that individual mean difference of 0 is really, really, really small. Well, unfortunately, this holds for every single probability of any single specific mean difference. What's the probability of sampling a mean difference of exactly 1 equals the area of a line, really small. What's the probability of sampling a mean difference of exactly 2? It's the area of the line. It's really, really small. What's the probability of sampling a mean difference of negative infinity? Even though we know it's unlikely in practice, but in math theory it's likely, it's the area of the line. So we're going to have to try something different with probability to start to find our quote-unquote p-value, to start to try to disprove the null hypothesis. And so this is where the precise definition of the p-value is important for your understanding where the p-value, what the p-value means and what it represents. So if you look in the next column, you'll see that the p-value is the probability of sampling a mean difference that is equal to or more extreme than the mean difference we sampled in our experiment if the null hypothesis were true. So there's a few things. We're sampling a mean difference from our experiment. We're assuming the null hypothesis were true. We're figuring out the probability of sampling a mean difference that is equal to or more extreme than the mean difference we sampled in our experiment if the null hypothesis were true. So we're going to have to use our random sampling distribution of mean differences when the null is true to solve this problem. So let me show you how we find p-values. So I sampled a mean difference of 0.5 in my experiment. The question is, what is the p-value of sampling a mean difference of 0.5? Well, let's translate that. What is the probability of sampling a mean difference of 0.05 or more extreme? For this problem, I'm interpreting more extreme as greater than, right? Greater than 0.05 if the null hypothesis were true. So essentially, now, the probability includes all the mean differences that are at exactly at 0.5 and all the mean differences that are greater than 0.5. So my p-value for this problem once again represents red over blue. And let's just eyeball it. That looks like 40% to me, right? So our p-value is 0.4 in this problem, right? That's what we're seeing. We're just eyeballing it right now, but that red area represents the p-value, right? We're using that random sampling distribution of mean differences that tells us the probability of sampling any mean difference from negative infinity to positive infinity if the null hypothesis were true. So the probability of sampling a mean difference of 0.5 if the null 0.5 if the null hypothesis were true is infinitesimally small. The probability of sampling a mean difference of 0.5 or greater is about 40%, and that's technically our p-value in this specific problem. So let's talk about interpretations of p-values. So essentially, if your p-value is less than 0.05, you have disproven the null hypothesis statistically. So I'm just going to do an example that's unrelated to the previous example. Our previous example was 0.4. You're going to see we know nothing in the second column of this specific slide. But let's say our p-value is 0.04. What do we know? We know that if the null hypothesis were true, only 4 out of every 100 experiments would find such a small p-value. That's what we know. And p-values come from mean differences, so such an extreme mean difference, right? We know that. That's very, very unlikely. So in this one experiment, we found this tiny p-value, and we only ran one study. And you know what? It's unlikely to find such a small p-value if the null were true. It's very, very unlikely. It's so unlikely that we are basically saying that the null is not true. We're saying we have statistically disproven the null hypothesis. And what does that mean? That means that we are pretty confident that our true population mean difference is not 0. It could be 0.001. Our true mean difference could be 0.001. It could be 1,000. It could be 1,000,000, right? But all we know right now, the only thing we know, is that our true population mean difference is not 0. I should technically say that we know that our true population mean difference is very, very, very unlikely to be 0. But let's talk about it in science and disproof, right? Right? We're essentially treating this as if our true population mean difference is not 0. That's how we write about our p-values. That's how we interpret our p-values in our fields. So let's not sugarcoat it. Yes, you're not supposed to say this stuff out loud, but when you're learning this, you have to learn this. You have to learn that with a p-value this small, we have disproven the null hypothesis. Whenever we have a p-value that is less than 0.05, we have disproven the null hypothesis, and we're saying that there's basically no way that the true population mean difference is 0. That's all we know. Now, when we compare this to what we know about 95% confidence intervals, you're starting to see, we know a lot more about the true population mean difference when we start to focus on 95% confidence intervals of the mean difference. With our p-value, we only know if we've disproven the null hypothesis. That is, we only know if we were saying that our true population mean difference is not 0. That's it. That's all we know. With the 95% confidence interval of the mean difference, we know so much more, right? We talked about that in the previous lecture, so I'm not going to say it here, but I want you to compare those in your mind. Which one's better, right? Knowing a range of possible population mean differences that are likely true, or just knowing that one specific mean difference of 0 has been disproven? Which one's better for a scientist to make interpretations of their data? Exactly. You should agree with me on that one. If not, then you're going to make wrong conclusions. People are going to use your research, your vaccine might not work at all and might lead to more deaths. So those are the serious things about it. Ultimately, what do we know when your p-value is greater than 0.05? You literally know nothing about the population mean difference. The mean difference could be 0, but we don't know this, right? Think about those 95% confidence intervals of mean difference that range from like -100 to +100, right? Their p-value would be greater than 0.05, right? It has 0 in the interval, but we don't know what that is. Blah, right? Also, you know what? Our true population mean difference could be a number that's not 0, and we just had bad methods. Our methods were too poor to see it. So essentially, we know nothing. When our p-value is greater than 0.05, we know nothing about our true population mean difference. Compare this to the 95% confidence interval of the mean difference, even when our p-value is greater than 0.05, when that interval includes 0. We know something. All right, so in terms of our definition of p-value, has the probability of sampling a mean difference that is equal to or more extreme than the mean difference we sampled if the null were true. We can interpret this in two different ways. In the previous example, we interpreted it in the one-tailed way, only in the direction of the effect that we found. This is not acceptable in our fields, so we're not even going to talk about one-tailed tests anymore. We use two-tailed tests. They account for the one-tailed effect, the effect in the direction we found, plus its mirror image. All your p-values in this class are two-tailed. Let's see what that looks like for the previous problem. So before, with the same problem, our sampled mean difference was 0.5, right? Our probability was only the right side of that line that's at 0.5, right? That was our p-value. Now, with a two-tailed test, our p-value doubles because we have to account for its mirror image. The reason for this is because, let's be real, if you found a significant effect in the opposite direction that you predicted, you might publish it. So essentially what we're saying is we don't trust humans to use a one-tailed test, and so we all have to use two-tailed tests. So that's it. That's how this is where p-value comes from. The red over blue fraction there is your p-value. That is your p-value. That's it. That's all you're doing. This is a fraction problem from 4th grade that's just a little bit complicated. You make one change. Leonardo made a bell-shaped pizza that fits the definition of the normal curve. This pizza represents the null hypothesis being true, so the middle of the pizza is at 0. Leonardo from the Teenage Mutant Ninja Turtles cuts one slice identified by a mean difference of 0.5. What proportion of the pizza is Leonardo eating? Well, Leonardo thought he was eating 40% of this thing, but Michelangelo came in and ate 80% of it because he thought it was a two-tailed test. Ha ha ha. This is not something to be scared of. It's a 4th grade fractions problem. So cowabunga, really realize that your p-value is an elementary fractions pizza problem where you have a weird shaped pizza. P-value is the probability of sampling a mean difference equal to or more extreme than the mean difference you sampled if the null were true, and this means two-tailed. We are psychologists, this means two-tailed. I need you to conquer your math fear here. P-value is not complicated once we understand the random sampling distribution of the mean difference when the null is true. So just a quick review. We're trying to disprove the null with our stats because disprove is considered by many to be the cornerstone of science. So this is how we statistically disprove ideas in science. This is how we differentiate ourselves from Freud. And what we do is we convert this null hypothesis to the random sampling distribution of mean differences when the null is true. And this random sampling distribution of mean differences when the null is true has a few properties. The mean of this distribution is 0. The building blocks, it's made up of mean differences. The limits are the infinity limits. The shape is normal. Those two are related. The standard deviation of this distribution is called standard error, and we use this as a probability ruler. We find the probability of sampling an mean difference equal to or more extreme than the mean difference we sampled in our experiment if the null hypothesis were true. This is our definition of p-value. We use a two-tailed test. We always use an alpha of 0.05. This is just a fractions problems from elementary school. And if our p-value is less than 0.05, right, that means that we are very, very unlikely to sample the mean difference we sampled if the null is true. We are so unlikely that we're saying we've disproven the null hypothesis that the true population mean difference is 0. I've simplified the homework. I hope it should take you about 10 minutes. I want you to draw a random sampling distribution of mean differences when the null hypothesis is true. Make sure you have all the properties listed under here. Want all of these correct. In terms of the standard deviation, just say standard deviation equals a vocabulary word that is the standard deviation of this specific distribution. Then I'm giving you one problem, okay? You got your picture, you got your null hypothesis presented in a picture. Now you ran an experiment. You sampled a mean difference of 20 and your p-value is 0.04. Add your sampled mean difference to your graph. Add your p-value to the graph, has a number in the appropriate shaded areas. I want to see it in the appropriate shaded areas. Make sure you're coloring in your mean differences in a way that lets me see the color fraction corresponding to your p-value. Yes, I want you to have a bunch of little circles in this distribution that represent your mean differences, because if you don't, students do not understand what they are doing. The random sampling distribution of mean differences, when the null is true, is a probability ruler made up of mean differences that tells us the probability of sampling any mean difference from negative infinity to positive infinity if the null hypothesis were true. Finally, I want to know, did you disprove your null? If you must say reject, right? Did you disprove your null hypothesis? Yes or no? And then finally, what do you know about the true population mean difference? You only know one thing. You don't know as much as you do with a 95% confidence interval of the mean difference. You only know it about one thing. I want to make sure you get that correct. So make sure you get that correct. The end of lecture, the end of this show.